All right, so we're going to pick it up where we left off yesterday. We're looking at the discussion about the differences between the mean and the median. And so we've seen that the times when you might want to use the median are the cases when you have an outlier or more, one or more. It's possible to have more than one outlier in your data. And we're going to see why that's so important. So the first one we did was introduce the concept of an outlier, and we saw that an outlier is simply an observation in our data set, whether it's a sample or a population, that is either much larger or much smaller than the other elements in the data set. And that can cause problems for the mean, but we'll see that it does not affect the median. And so these are the cases when using the median is probably your best bet for coming up with a measure of central tendency. So, for example, here you can see very obviously that in this sample, the 100 at the end there, x6 is 100, that is our outlier. Now, what if we decided to calculate the mean of this sample? Well, you can see that we'll just add up all 6 values, we add them up, divide by 6, and we end up with 19. Now, the problem here is that 19 is larger than all the values except for the 100. So it doesn't give us a very good look at the center of this data, even though that is technically correct. It's very deceiving because almost all the observations are smaller than 19. Only one is larger. So it's very deceiving. On the other hand, if we calculate the median, the first step, of course, as usual, is to sort the values from low to high. And since there are 6 observations, as we saw yesterday, we're going to average out the 2 in the middle, which just by coincidence are both 3s. And so we end up with the average of 3 and 3, which is 3. And so you can see that with this data set, the mean is 19, but the median is 3. I think you'll agree that in this case, a median of 3 is a much better or realistic indicator of the center of this data set than the 19. And to make it even more interesting, what if that last value was not, let's say, 100, but 1,000? Well, then the average would have been even that much higher. In fact, it would be really high. What would it have been? 1 plus 2 plus 3 plus 3 plus 5 plus 1,000 divided by 6, 169. And that's even more unrealistic. But guess what? The median would still be 3. It doesn't matter that we have this 1,000 here as an outlier because the 3 is still at the center of the data. So in other words, you can see here that outliers, and by the way, that applies to very small ones as well. If we had a very small number down here, for example, it would distort the mean, but not the median, because the median is the halfway point, regardless of how large or small the observations are. So the conclusion to all this is that when we have situations where we have potentially at least one or more outliers, then the median is probably a better choice for the measure of central tendency. The rest of the time, we typically use the mean because it's easier to understand what it actually is telling us. In other words, interpreting the mean is a little bit easier than the median. And as we go along in the course, we'll see that in a lot of other types of situations, we'll need the mean as part of another more advanced measure. So the mean is still probably the more widely used of the two, but you can see that in these cases, the median is a better choice. All right, and then finally, as we briefly mentioned, the mode is simply the most frequently observed value in a sample or population. So with numerical data, we don't use this very often. I mean, sometimes it can be useful, but it's not nearly as important as the mean or the median. So one of the bizarre things about the mode is that unlike the mean and the median, where there's a single mean or median, there doesn't have to be a single mode. In fact, there can be 2 or more modes, and there can be no modes at all. And so that sort of reduces the value of this measure. It makes it even trickier to interpret it. But let's look at an example of this. We have these 6 values, and so we're going to sort them out from low to high. Not that it's absolutely necessary, but it will be easier to see which values are repeated the most often, especially if we have a larger data set. So we'll do that here. And you can see there's only one value that's repeated, and that's the 3. And so therefore the mode of the sample is 3. And that's all there is to it. Now here's another case. Let's say we have another sample and the sorted values look like this. Well, you can see there's a tie for first place, so to speak. In other words, the most frequent values are the 2 and the 6. So we say that 2 and 6 are the modes of the sample. So there's 2 of them. And so we describe this data set as bimodal, where clearly the bi means 2. All right. And you can have 3 or 4 or 5. There's no limit to how many modes we can have. On the other hand, look at this case. Not one of those values is repeated. And so we end up with no mode at all. There doesn't have to be a mode. Okay. Oh, by the way, one more piece of terminology here. If a sample or population has a single mode, we call it unimodal. Uni meaning 1. Okay. And bi, as we just mentioned, for 2, where bi, of course, equals 2. All right. So now, oh, and by the way, just like with the median, there is no actual formula for calculating the mode. It's just a series of steps. Okay. If you notice, we didn't show a formula here. And furthermore, in this case, we don't need to make a distinction between a sample or a population because the procedure is exactly the same in both cases. Right. So unlike the mean, where there's a formula for the sample and population versions, here we don't have either of those things. We just have a series of steps that we will follow. All right, now we're going to introduce an important idea here. We can draw information out of a sample or a population by just looking at the values of the mean, median, and mode. And what we'll see is that given the relationship between them, there are 3 basic situations that can arise with our data. The data can be what's called negatively skewed, it can be symmetrical, and it can be positively skewed. Now, a lot of data sets don't fall into any of these 3 categories. So in other words, it's not the case that all data sets must be one of these 3. In fact, it's kind of unusual to find these 3 cases. But when we do, it's important to understand how these properties work. So let's see, what is this all about? So, by the way, I just want to remind you, the word symmetrical, just in case you've forgotten what it means. Let's say symmetry refers to a situation where there is a balance. Often, let's say, for example, let's see. Imagine that you had a building. I don't know. Let me see if I can draw a graph. Rather than, I'll do this. Let's say this is a histogram or a data set. Now, histogram is a series of bars that represents the data that we have. And so let's say we have some data set where this is what it looks like. Oops. Okay, now it's not perfect, but what I'm trying to indicate here is that 0 is in the center of this distribution. If you notice, remember the heights of these bars represent frequencies. How many times this occurs. And then this is just some X. It could be anything. It could be temperatures. It could be anything you could imagine. So what this is telling me is that 1 and -1 occurred an equal number of times. 2 and -2 occurred an equal number of times. And I can tell because of the heights of the bars. And then 3 and -3 also occurred the same number of times. So we say, if you can imagine drawing a line down the center, what's happening on the right-hand side exactly matches what's happening on the left-hand side. In fact, you can think of the two sides as mirror images of each other. And so this distribution is symmetrical about the center. Or mean. Okay, so that's what symmetry refers to. There's a balance of some kind. The area to the left of the mean is the same as the area to the right of the mean. They're mirror images of each other. The other two cases, skewness, means it's not symmetrical, but the way in which it's not symmetrical is important. Okay, so let's take a look at these graphs and we'll see what this is all about. So negatively skewed occurs when the mean is less than the median, which in turn is less than the mode. Now, this often results when you have a data set where you have a handful of very, very small or negative observations. You might, in the real world, you might run into this with, let's say, a portfolio of bonds, because what can happen with bonds is the issuer can go bankrupt, and then the bondholders get a very, very negative rate of return. So, and this does happen periodically. So in a data set which represents the returns to a bond, you might find this happening because there's going to be a lot of positive and negative returns, and then an occasional enormous loss, which will cause the mean to be smaller than the median and the mode. So let me show you what this graph looks like. Now, this is meant to indicate the returns to a stock. And the bars, this is our histogram. And what you notice is on the horizontal axis is rates of return, which range from negative 8.5% up to positive 4.5%. And so I've drawn a line here to indicate, if you notice, the left side has a lot more values than the right side. What this means is that this portfolio had a lot of losses, but not quite so many gains. There were gains, but there were a lot more losses. And the losses themselves, if you notice, the largest loss is 8.5%. The largest gain was only 4.5%. So this is not a portfolio that we want to own. That's for sure. So, oh, and these are the frequencies with which these returns happened. So we call this negatively skewed. And so we describe this graphically as a long left tail, it's called. Okay. And we have a short right tail. In other words, you don't have a balance between the two sides. There's a lot more negative observations than positive. And so we call this relationship negatively skewed. Okay, so this is the one you don't want, with at least with your stocks. Now, a symmetrical relationship looks like this. The three measures are equal to each other. So we're going to get a nice symmetry between the two sides, the gains and the losses. What's this going to look like? Oh, there you go. Now that looks really nice. So you can see there's a perfect balance between losses and gains. Ah, okay. In other words, the two sides are mirror images of each other. And this is what we mean by symmetric. We can think of this as symmetric about the mean. Or sometimes we can just describe it as being symmetrical. And this will be the case when the mean, the median, and the mode are all equal to each other. And then finally, the last possible case is what we call positively skewed, which is just the opposite of negatively skewed, as you can imagine. And that simply means the mean is the largest value, followed by the median and the mode. So this is the case that you're happy about, because if you're the owner of the stock or a portfolio, your gains have outnumbered your losses. And furthermore, you have some pretty nice large gains in here. The smallest or the worst loss is a loss of 5.5%, but you do have a gain in here of up to 7.5%. So this is what you're hoping for when you own stocks or any investment. We call this positively skewed. So that means that this is happening. Now, like I said, I don't want to give you the impression that this is true for all data sets. Many data sets do not fall into any of these categories. So let me just show you a sketch of something that would not be one of these. Let's say this is your histogram. Well, that you can see, well, that's a very extreme example. That obviously does not fall into any of those categories. It's not even close. Okay. So yeah, it's not the case that all data sets have to fall into one of those three categories. Okay. Now, up to this point, we focus all of our attention on the measures of central tendency. And so imagine yourself as a stockholder. It's important to understand the mean return that you might get from holding a share of stock. What about, though, there's another consideration you want to think about when you own stock. It's not just the average rate of the return, but you want to know how much risk is involved. Okay, because you know perfectly well that even a stock that averages, let's say, 8% per year can have a rough year. How do we know how much we could lose in a bad year? Or how much might we make in a good year? That's important too. It's not enough to know the average. The average is fine as far as it goes, but it's not a complete piece of information. In fact, let me just show you a quick example of two stocks. And what you're going to see here, let's see. Let me just insert a table real fast of what I mean by this. Now, here's one of the things I've always wondered about with Microsoft. They sometimes make the strangest choices about the default choices. If you notice, when you choose a table in here, the default choice is green. Why green? Who uses green tables? I have to search to find what I want, which is just a plain old table. I don't know what's wrong with those people, but anyway, so you've got two stocks. So let's say stock X has had the following returns over the last 5 years. Okay. Actually, let me make that a little bit bigger. All right, there you go. And when you try to fill it in, it assumes you want green. All right, so that's the first stock. Now, what I'd like you to notice here is that the average return to that stock over the last 5 years, if you add those up, it's actually 2%. Okay, in other words, if you add up all 5 of these observations, it adds up to 10%. So since there's 5 observations, we have an average of 2%. Well, let's try this one. Okay, so if I've done this correctly, let me make sure, because I'm just making this up on the spot. Yeah, it's 10. All right. So in other words, the average is 10, 2 rather. It's 10% total divided by 5 years. So what I'm trying to illustrate here is that the two stocks each have an average rate of return of 2%. But you'll notice something really important here. StockX is very stable. The lowest return in that time series is a loss of 1%. And the best, though, is only 3%. So this is a stock for somebody who really wants to play it safe. Stock Y is all over the place. It goes as low as negative 26% and as high as 28%. So I think you'll all agree that stock Y is a lot riskier than stock X. So since the returns to Y deviate significantly from the mean, 2%, stock Y is considered to be much riskier than stock X. Now, that means that if they both have the same mean return, everybody will choose stock X because you're getting the same average rate of return. So let me just make a note here, though. In practice, the riskiest stocks also tend to have the highest average return because otherwise nobody would buy them. Okay, so in other words, this is an artificial example because in practice, a stock as risky as Y would certainly have a much higher return. Otherwise, nobody would buy it. Then the price would fall and the rates of return would go up. So what we want to see here, though, is that stock Y's returns on average are further away from the mean than stock X. So that is obvious from the table, but we'd like to have a number that we can assign to each of those two stocks, which helps us quantify how much riskier Y is than X. So a set of measures has been created to determine how much a variable deviates from its mean on average. These measures are known as measures of dispersion. So I think, as I was saying before, knowing the average return of these two stocks is not enough for you to make a decision. It's also important to take into account how risky the stocks are. And if you're not willing to put up with all this risk, then you probably would want to buy stock X. Even if stock Y had a higher rate of return, you might still avoid it because there's so much risk here. Okay, but the bottom line here is we need a measure that helps us understand how spread out the data are. Now, I also want to show you with a histogram how, we can visually see how spread out the stocks are, the returns are. So this is just meant to be a rough sketch. What do we have in here? -1, 2, and some 3s. Whereas the second stock, oh my God, we were all over the place. Okay, -26, -24, +14, +18, and 28. Wow. All right, so this is not a great drawing, but what I want you to see is with the histograms that stock-wise returns are much further spread out from the center, which is 2%. Okay, so therefore Y is riskier than X. So we'd like to have a number that we can attach to each of these stocks so we can compare them side by side without needing to go through all of this every time. So these are the, all right, here's another example that I thought of. Look at these two samples. These could be anything. They're not necessarily stocks. But the idea here is that sample 2 is very spread out from the center compared to sample 1. So the measures that we'll be considering here, there are several of them, to measure dispersion are the following. We have the range, we have quantiles, we have variance, standard deviation, and coefficient of variation. Now, you've certainly heard of the range before. It's an easy measure. It's not the best, but it's quick and easy. It'll give us a good idea of how much dispersion there is in our data set. The two that are really the most important in this group are right here. And in particular, we'll see that this is the one that is the most commonly or widely used as a measure of dispersion. It has a lot of important advantages. The only drawback is that it's fairly complicated to calculate it. But that's often the case with statistics and math. The more useful a measure it is, chances are the more complicated it is to calculate. Oh, well, but we really still need it. Anyway, so we'll start with the range. The range is a very simple idea. It's simply the difference between the largest and the smallest elements in either a sample or a population. So here's the data set we saw earlier, a sample of 2, -1, 3, 5, and 1. Now, for the range, we'll note here that just like the median and the mode, we have to sort the data. And it turns out there's no formula. Oh, well, I mean, I guess you could make the case. There technically is a formula. You could just write it as the range is the maximum value minus the minimum value. So I guess you could claim that there's a formula, but we don't, not like with the sample mean where we had a nice elegant formula. It just means the difference between the largest and the smallest values. Also, it's the same for both samples and populations. So let's sort these out. And of course, here's our maximum. Here's our minimum. And so all we have to do is take the difference between the two, being careful because we're subtracting a negative number. And so we end up with 6. Okay, 5 minus -1 is actually 6. All right. Now here's another one. Let's say we have a group of students in a class and we wrote down their GPAs and we sorted them. So what would be the range here? Well, clearly this is the maximum and this is the minimum. So the difference between the two is the range. And so you can think of a lot of examples of this. So it helps us understand how spread out the data are. And in fact, if we went back to this previous example with the stocks, you could see that the range for stock X is only 3 minus -1. That's a small range. Whereas for this one, it's 28 minus -26. %54 is the range for stock Y. You can see, so the difference is enormous. Okay, so you can see numerically now that the range for Y is quite a bit higher than for X, which tells us that stock X is a lot riskier than Y. Y is riskier than X. All right, so we'll use this. It's a good first approximation. It doesn't give us quite as much information as some of the other measures. Here's one that you might run into from time to time. It's called quantiles. So basically, this is a way of breaking up data into equal parts. And so let's take a look at three ways we can do this. And I'm sure you've heard of some of these before, especially percentiles. This divides the data into 100 equal parts consisting of 1% of the total. So let's just say that you take an exam and you're told that you're in the 92nd percentile compared to the rest of the class. That means you did better or scored higher than 92% and lower than 8% of the data set. That's pretty good, 92%. Being in the 92nd percentile means you did extremely well. So that number tells me within the data set, sorted from low to high, by the way, how did I do compared to everyone else? 92% did worse, 8% did better. And when you take standardized exams, they'll give you a raw score, which represents how many you got right. And then they'll give you a percentile, so you know where you stand compared to everyone else. Okay, like the SATs, for example. You might remember, let's say, on the math part of the SAT, if I remember correctly, it only goes up to 800. So let's say you got a 750. And you might say, well, that sounds pretty good, but I don't know how I did compared to everyone else. And let's just say this turns out to be the 96th percentile. Well, now you know you really did well because it's only 4% and better than you did. See, in other words, this tells me more than this does. I mean, as far as comparing myself to everyone else, 750 is nice, but it's hard to say. If this was a particularly easy test, 750 might only be in the 50th percentile, for example. So the fact that it's 750 puts you in the 96th percentile tells you how difficult this test really is. Then we have deciles. Deciles are a little different. All you're doing here is breaking up the data into 10 equal parts, each of which represents 10% of the data. So in other words, just as an example, oh, it would help if I spelled it right. The 9th decile. I did it again. Would be equivalent to the 90th percentile. You don't see this as often. You might use this when you don't need to be quite so precise. See, this way you're only getting like 90, 80, 70, for example. And then the quartiles, when you only need to break people up into fourths. The first quartile Q1 is the 25th percentile. The second quartile would therefore be the 50th percentile. And by the way, that indicates that this is also equal to the median. Whereas the median is just another name for the second quartile. And then finally, the third quartile, Q3, is the 75th percentile. And then we don't normally define a fourth quartile. It would have to be 100th percentile, which would simply be the maximum in your data set. Most of the time, we'll focus our attention on these three quartiles. Okay, so the question is, how are they calculated? All right, that depends. There's two cases we might encounter: an odd number of values and an even number of values. And the reason why we're doing this is because quartiles are closely related to the median. If you recall, the process for the median depends on whether we have an even or odd number of values. So let's consider the case where there's an odd number of values. So we have 1, 2, 3, 4, 5, 6, 7 observations. So this is my median, and it's also my second quartile. Well, this is a very simple case because the first quartile is the median of this lower group, and the third quartile is simply the median of this upper group. Oh, I'll just call it the upper half of the data. Whereas Q1 is the median of the lower half. Of the data. And Q2 itself is simply the median of the entire data set. Well, that was easy. Now, there's just one problem. What if we have an even number? Okay. So we're going to calculate, first of all, our median or second quartile is the average of these two. 3 plus 4 over 2 is 3.5. So what we have to do now is think of the lower half of this data as being these, and this is the upper half. So there's the lower and the upper half of the data now have an even number of values. So Q1 will be the median, which means the average of these two. And that also means that Q3, whoops, I'm taking the 2 in the center. So it's the same thing we did yesterday with the medians, except we're breaking the data set into two halves. And once we have those two halves, then we find the median following the rules, depending on whether we have an even or an odd number of values in the upper and the lower half. So this is exactly what we were doing yesterday. Okay, now we're going to tile this together with a very important measure, which is called the interquartile range. And it's a very simple measure. It's just essentially the middle 50% of the data. Q3 minus Q1. So if you can imagine, there's a line that represents our sorted data. The interquartile range is everything in here. Okay, the average people are in the middle, all right? People who are not way at the top or way at the bottom. Now, interestingly enough, I did mention yesterday actually that there is a formal definition for finding the outlier of a data set. Remember, we decided that when there's an outlier, we're better off using the median than the mean because outliers distort the mean. Well, for this particular type of situation, one of the best ways to identify outliers is with the following. Remember, there's two different ways we can have outliers, ones that are much larger and ones that are much smaller than the rest of the data. So we're going to define the upper limit for an outlier as any number that's greater than Q3 plus 1.5 times the interquartile range. For the lower limit of what is an outlier, well, if anything below Q1 minus 1.5 IQR. All right. That now, by the way, even this is just an approximation. It still isn't quite as rigid as this, but it's a very good indication. So it's you think of it as a rule of thumb. About here is where you would expect to see outliers. Now, what I'd like to do is return to that last example and find what outliers would have been if there were any. So based on the last example, so remember just a minute ago, in this case, we had 1.5, 3.5, and 5.5. Whoops, my bad. So for the outliers, oh yeah, one more thing, the IQR is 4, because that's the difference between these two. So anything above 5.5 plus 1.5 times 4 would have been thought of as an outlier, or less than Q1 minus 1.5 IQR. 1.5 minus 1.5 times 4, negative 4.5. So in other words, any number, if we had any values in our data set that were below 4.5 or above 11.5, we could have thought of them as outliers. Now, we didn't have any of those. You can see the numbers are all between -2 and +7. So there were no outliers in this data. But if that 7 had been, let's say, a 12, well, then we would have had an outlier, because the upper limit is 11.5. Or if this -2 had been -5, that would have been an outlier. All right, so there you go. So we have some value from this. These quartiles are helping us define and identify what does and does not count as an outlier. All right, now let's take another look at this list. We're ready for number 3. Now, I mentioned variance and standard deviation are the two more important of these measures. It turns out that they're not actually two separate measures. The standard deviation, as we'll see in a few minutes, I might as well mention it now, is nothing but the square root of the variance. So when you calculate the variance, it's easy then to come up with the standard deviation. And we'll see why this is happening in a few minutes. Now, another thing I want to point out is that for the first time in a while, we're going to need formulas again to describe these two measures. And these formulas will be different for samples and populations. We've been we had several measures in a row: the median, the mode, the range, the quantiles, which aren't really formulas. They're procedures, and they're identical for samples and populations. Now, for the first time in a while, that will not be the case. Okay, so we'll start with the sample variance and we'll take it from there. So let's show you the formula. And let's interpret it. Oh, now that looks just a little bit more complicated than what we were doing yesterday. S squared is used to represent the sample variance. Remember, X bar is the sample mean. This Xi is a single sample element indexed by I. Of course, N is the sample size. Now, this numerator, what it's telling me is to go through all the elements of my sample, in each case subtract the mean and square the difference before I add them up. And now remember, we went through these different examples for the summation operator. Remember this one? This is the last one we did. It's Xi minus K, where K is a constant. X bar is a constant. So these are the same case. So that's why we did that, because we wanted to be prepared for this when it showed up, because that is exactly what we're doing. So this is more, I'd say, more messy than complicated. All right, here we go. Let's do an example of this. So here's the sample we've been using for a while now. And we calculate the mean, which we've already done, and we determined that that was equal to 2. Now, the formula for the variance tells us to do this. We're going to go through the list. So let me just quickly remind you that what you have here is x1 minus x bar squared. This is x2 minus x bar squared. This is x3 minus x bar squared. This is x4. And then finally, this one is x5 minus x bar squared. So the tricky part here is just simply substituting incorrectly. It's easy to mess this up. You can see there's lots of opportunities to make mistakes, and I mean lots. So if you get this part right, you're in good shape. Now we just have to evaluate it. So what you should probably do is solve for these differences first before you square them, because otherwise it's easy. Well, let's just say if you skip steps, you might speed things up, but you also might make mistakes. Okay. Now you can square all the terms and add them up. All right, so I'm going to copy this onto the next slide, just as a reminder. And so you can see we're going to have 0 plus 9 plus 1, 9, 1. So we end up with 20 over 4, which is 5. All right, now, what about the standard deviation? I did say that these two are closely related to each other. So the sample standard deviation is nothing but the square root of the variance, the sample variance, I should say. So this is what you're doing. So remember that S squared looks like this. So all I'm doing here, this is S by itself, is the sample standard deviation. So literally, whatever I had in the last part, remember this was 5? That implies that S is simply the square root of 5, which is approximately 2.236. So that raises an interesting question. Why are we doing this? Why don't just stick with the variance? Good question. There's a very good reason for it. The drawback to the variance is that it is measured in squared units. So for example, if the data refers to temperatures, then the variance would be interpreted as 5 degrees squared. What does that even mean? Well, it doesn't really mean anything. So standard deviation is interpreted therefore as 2.236 degrees. So the advantage of the standard deviation is that it is measured in the same units as the actual data that we're working with. So why don't we go directly to the standard deviation? Well, the thing is, you have to calculate the variance first in order to get to your standard deviation. So that's why you can't just say, well, what the heck, let's just get rid of the variance. You need that first in order to actually calculate the standard deviation. Now, I just want to mention here too, this is a very popular measure of risk in the financial markets. The standard deviation, the stock's returns, known as the stock's volatility, is a very popular measure of risk in the financial markets. You see this all the time in finance in particular. Standard deviations are used to represent the risk of holding not just stocks, but any other assets you might have and own, but especially stocks. The word standard deviation, sometimes it's referred to as the volatility, and that tells me just how risky my stock is. And that I need that information to make a decision about whether I should own it or not. Now, for the population variance, the formula will be different. And let me just quickly write in here what the formula looked like for the sample version. So I want to point out that there's not just notational differences. By the way, this is the Greek letter sigma, but it's the lowercase sigma, as opposed to this one, which is the uppercase sigma. So sigma squared is the variance of the population. Mu is the population mean, remember. Okay, so it's mu, but it stands for the population standard, the population mean, that is. And capital N, as you recall, is the size of the population, or think of it as population size, to distinguish it from lowercase n, which tells me the sample size. So now, all of a sudden, unlike with the means of the population and the variance, which were algebraically identical, but with different symbols, all of a sudden, for the first time, you can see algebraically there is a difference. So we've got different notation, and we have slightly, and I mean slightly different formulas algebraically. is the first time we've seen this. Okay, so they're not the same. Now, what this tells you is that when you're doing problem sets, it's awfully, awfully important to make sure you know whether your data is a sample or a population. Because if you don't, you're bound to guess wrong. It's just that simple. So, and then of course, as you can probably imagine, the population standard deviation is simply the square root of the population variance. Okay, so just a minute ago we saw, oops, let's stick with black. So in other words, if this is the variance, this must be the standard deviation. And you'll see this many times throughout this course and in stats decision making. We'll have a variance of some kind, and we know that no matter what circumstances we're in, the standard deviation is always, always, always the square root of the variance. That never, ever changes. All right, so we don't really need a separate example of this. Instead, we're going to jump ahead to the next measure, which is called, this is the last in our list, by the way, of measures of dispersion. It's called the coefficient of variation. And this one unusually actually combines a measure of central tendency and a measure of dispersion, creating what's called a measure of how the members of a sample or population are spread out compared to the mean. How does this thing work? Well, whether it's a sample or a population, we're taking the ratio of the standard deviation over the mean and multiplying by 100 to turn it into a percentage. So for a sample, you'd have this. The population version would look like this. Remember, the rule of thumb is that the Greek letters are used to represent populations and the Roman letters are used to represent samples. All right, so let's look at a quick example of this. This is a completely new example. We have two portfolios of stocks. We're going to think of the returns to these as populations, two populations, populations A and B. The first population, we discover that the mean return to those stocks is 8%, and the standard deviation is 16%, which we'll express as decimals. For B, I'll just fill these in here for you. There are 10 and 30% respectively. So what this tells me is that B, meaning portfolio, I guess I'll call it portfolio B, has a higher mean return, but is riskier. How do you know that? Because the standard deviation is higher. So then you want to ask yourself a question: which one of these should I pick? Am I willing to tolerate all that extra risk from portfolio B? Is the 2% increase in the rate of return enough to justify all this extra risk? So these are the kinds of questions that we can answer with the coefficient of variation measure. So let's do it. So for A, plugging in those numbers, you'll see that your coefficient of variation for A is 200%, which means that the risk is double the average return. That's what it means. What about B? Doing the same thing. You can see that, oh, wait a minute, the risk is triple the average return. Oh boy. So with this measure, it turns out you want to pick the one with a lower CV. Why? Because remember, the CV represents risk to return ratio. So therefore, we're going to pick A. Even though it has a lower return, only 8% versus 10, the risk is so much lower that we're better off with A because the amount of risk relative to the return is lower. Or think of it this way, the extra risk we need to take on portfolio B does not justify the extra 2% rate of return that we're getting. Okay, now in this chapter, we have a third type of measure that we want to consider. We've already done measures of central tendency. We've done measures of dispersion. The third and final set of measures is a little bit different because with these measures, we're comparing two different samples or two different populations. So the calculations will be messier, but this is awfully, awfully important. And we'll see more about that in our next section. So for today, I think we've had enough. We'll stop right here, and I'll see you next time.